the last class, we discussed some examples of frameworks as an example of systems under mechanical equilibrium. In that case, the emphasis on the examples that we learned, the emphasis was on to calculate the unknown forces at the support, the contact forces at the support or the tension forces along the beam or an element of a truss. Today, we are going to look at a slightly different question. So, we are going to ask what, given a system of framework or a truss, and there are a lot of unknown forces which are the forces that are acting on the joint or a contact or a support, or the forces, the tensions, the internal forces that is acting on the beam. So, these are the unknown forces. Only thing we know is the external load acting on the framework and maybe the weight of the load itself. So, we ask now that what is the condition that we can determine all these unknown contact forces or tension forces uniquely. So, what is the general principle? So, the general mathematical principle is very simple. So, if you have the number of this a bunch of unknown forces, then you need to supply some equations, and if you have enough number of equations, then you can solve this equation and find the unknown forces. So, that is the principle. So, what are the sources of these equations? So, suppose this truss or a framework is made of n joints. In that case, for each of the joint, so this is what we learned in the previous lecture working through the examples, that in order to compute the unknown forces, you have to go node by node or joint by joint, and if you take your joint as your system and everything else is the surrounding, then you can write down two equations which are equations of force balance. So, I am talking, so what I have in mind here is a 2D truss. So, this is a condition in 2 dimension where all the forces are in this acting on the same plane. So, you can write down two equations of force balance per joint. So, let us say if you take this as your, let us say x axis and this as your y axis. So, if you choose this Cartesian coordinate system as your coordinate system, then you have a force balance equation for all the forces in the x direction. So, sum over all force in the x direction, x component of all the forces is 0, and similarly sum over y component of all the forces as 0. So, these are the two equations that you can write down for one node or one joint. Now, if there are n joints, then you have total 2n number of equations. Now, these equations, now if you consider the full truss structure as a whole, like then you are right now you are looking at only the external forces. Then for the whole structure, again you can write down two equations of force balance, as well as you can choose a pivot point, and then you can write down an equation, one equation for torque balance. Why one? Because from the, remember the definition of torque. So, if all the forces are acting in the same plane, the torque is going to be a cross product of the location of the force, line of action of the force with respect to the pivot point and the force itself. So, the torque is the moment, the torque or the moment of the force is going to be perpendicular in the direction normal to the plane. So, you have only one component of moment, it is a simple situation. Now, why did not we write down the equation of force balance for a node? In that case, you can simply think of this way. Let us say that we take the node itself as the pivot point, and then we are looking at all the forces that are passing through that node. So, they as we have learned before, that the torque due to each of those forces should be 0 about that node itself. So, the point is that for the entire Truss structure, then you have two equations of force balance and one equation of torque balance. So, total 3 equations. Now, these 3 equations, because you can sort of write down the these 2n equations for each node, then these 3 equations are sort of not independent. For if you sort of combine all the total 2n equations for each of the node, then you can show that you will it also already includes these equations of force balance. So, this we have seen in the example that we have worked out last time. So, the number of independent equation is actually not 2n, but 2n minus 3. Now, if there are how many unknowns? So, if there are m beams or truss elements, then and we assume with all the terms and conditions that we discussed in the last few lectures, that we are going to assume that only internal force is acting along the length of the beam, then only thing that is so the direction is known. If I know the truss structure, then the direction of the force, tension force is known. Only thing that is unknown is the magnitude. So, there are m unknown magnitudes of internal tension forces. Here we are assuming that the beams are massless, so we can ignore and all other elastic forces. So, then we can have m unknowns and 2n minus 3 equations. So, then we have 3 possibilities. The first situation is m, the number of unknowns, is less than the number of equations. In that case, it physically means that there are less beam or truss element than necessary. So, this is a case where the structure is unstable and may collapse under external load. If the m number of unknown forces is equal to number of equations, then we can solve. So, these are algebraic equations. So, we can solve those equations and calculate all the unknown forces, unknown magnitude of tension forces uniquely. In that case, we say that the structure is rigid and statically determinate, because we can compute, we can determine all the unknown forces. The third situation is where the number of unknowns is greater than the number of force balance and torque balance equations. How is that possible? It basically means that there are more beams than necessary. So, the minimum number of beams that is necessary to make the structure rigid, or rigid means in the sense that it can support the external load, but then you can always add more beam elements given this minimum structure, and then you have a arrive at the situation where m, the number of unknowns, is bigger than the number of equations, which means that some of those beams are redundant. That means that if you remove some of the beams, the structure will not collapse. In this case, all internal forces cannot be determined uniquely, because you have more number of unknowns. So, this situation is called statically indeterminate. Now, here I want to sort of mention a nice piece of history, and this is something that I want to say because it illustrates nicely the relation between the engineering point of view and the physics point of view. So, this the framework, as you know, designing a framework and suspension bridges, roofs, etc., are very old. So, it is a very old engineering problem, and engineers like civil engineers and mechanical engineers who have the task of building those structures. So, they are focused, or they are interested to know that what are the forces acting at each of the support, how much force a support can withstand, and so on. Now, there is a Maxwell, James Clerk Maxwell. He was a famous physicist. So, so he is the same Maxwell who you studied in the Maxwell's laws of electricity and magnetism, and those of you who are taking thermodynamics and statistical mechanics course, they will be studying about Maxwell's relations. So, it is the same Maxwell. So, he considered this problem, and he wrote a famous paper which is very old, published in 1864 in Philosophical Magazine, and I have provided the link so that if you are interested you can go and check that paper. It is available in online. So, he considered this same problem on the calculation of the equilibrium and stiffness of frames. So, frame is same as truss, but his focus was on a different question. So, this he posed an interesting question. So, he was not interested in calculating each individual unknown contact force, but he was interested in sort of devise a general principle by which you can address this question. So, his first question is that what is the minimum number of sticks required per joint to make the whole framework stiff. So, this is a kind of typical question that physics point of view. So, physicists always try to work out try to find out a general principle which can apply to all situations, whereas engineering point of view is to take a specific example and find out the specific design criteria, or for a particular design the specific like solving the unknowns. And he went on, and then he sort of gave a general method of how to solve this problem. If you look at from a general physical point of view, which is applicable to all sorts of design, which any framework. Now, I mentioned this thing because in modern times there is this particular approach, and this. So, let me mention this. So, this particular criteria that we found discussed. So, this is nowadays called Maxwell's criterion. So, now I mention one more example from not from from civil or mechanical engineering, but maybe perhaps relevant for chemical engineering and definitely physics. So, this Maxwell's criterion, Maxwell's way of approaching this problem nowadays finds a very surprising application in a particular field which is called the powders. So, if you want to study structures made of powders or also like grains like sands. So, sands and powders are very common material, it is there everywhere around us, but they are somewhat unusual form of matter. Why? Because as you know from experience that sand can flow. For example, the sand in a sand clock flows like a liquid. However, if you put a lot of sands in a high density packing, then they can also form rigid structure such as a heap of sand, like a heap of rice or heap of food grains. How do we know that this forms a rigid structure? So, next, for example, if you take a bottle of, let us say, sugar, and you try, and if it is well packed, then if you try to insert a spoon inside, it will prevent. So, it can support external force that is exerted by you on the this heap of sugar. So, they, in that sense they are rigid, and this is also a picture of a sand art, which is so definitely a rigid structure. Now, these kinds of materials, so sand is an example of a powdered material. So, powdered materials are very important. For example, let us say because a lot of chemicals are produced in a powdered form, such as cements, or even if you take a like the capsule, the medicine that you take as a capsule, the medicine is put in the capsule in powdered form. So, it is an important question in those kind of situations from practical point of view, is that under what condition a powder will behave like a solid or a rigid body, and under what condition it will behave as a liquid, and that is it can flow. Now, I must mention one more thing, that sands or powders are not conventional liquids like water, because their flow properties are very different from a typical liquid like water. They are also not a conventional solid in the sense that remains a solid body only when you can sort of compress them enough so that they achieve a high enough density, and you have to held them in a rigid form by external force. If you remove those external forces, then they may fall apart and they no longer behave as a solid. So, this is a different from your usual solids that you see around you, but they are very important engineering materials. So, for like from chemical engineering perhaps, and because of these interesting properties, they are also very interesting for physicists to study. And in this case, the method that we learned about truss or framework has an analogy in this case. So, what I show here is a simplified model of a granular material. So, think each grain like a sand, the different grains has different shape. So, here I am each grain is represented by same shape, they are all spheres, or let us say if you think 2D, they are all discs. And the red lines are, so when the two discs are in contact, they form a contact force. So, these red lines represents the contact force, and thicker the line, the bigger is the magnitude of this force, and the direction of the force is assumed to be along the line joining the center of two discs. Now, you can, if you look at this picture of the forces, so you can see that they actually look like a truss or a framework, and in fact you can use the same sort of analysis to sort of get to use these force balance conditions etc., to analyze the condition of rigidity of or properties of this kind of granular structure from our truss point of view. So, this is something I wanted to mention, because usually when you think about truss or framework, you think about something like a crane or a bridge or some such man-made structures, but here I show that these kind of concepts can also be used to study various natural phenomena such as the properties of granular matter. So, now we want to discuss another important point about the truss. So far what we assumed, the problems that we worked out, we assumed that these external loads are acted as a single point, such as for example, so we had this the bridge and there was a car on the bridge, and we assumed that the car is acting at one of the joints. But in many real life situation, this is not very realistic. So, more common perhaps will be that these external loads are distributed over a region. So, there is a distribution of external load. For example, here are few simple examples. Let us say this block represents a beam, and then these red arrows represents the profile of the external load. So, in the this case, as you can see that all arrows are of same height, that means the external load is uniform and it is distributed over a length L. In this example, the arrows are not of equal height, which means that the force profile is not uniform, but if you sort of join the details, so you can see that it is linearly. So, it is starting from 0 at one end of the beam. Let us say this is at one end of the beam, and it starts at 0 and then it linearly increase. So, the load at a distance, let us say this is our origin and this is our x axis. So, then the load at a distance x is proportional to the distance from the end. And this is a slightly more complicated example. So, here is again the load is increasing linearly with the distance from one end. However, in this case the difference is that in this from the middle example is that in this case at the end the load is not 0, it is non-zero. So, you can think of this as kind of combination of the first example and the second example. Now, it is not required that this load profile need not be linear, it can be non-linear also. Now, in the non-linear there could be lot of infinite number of possible load profiles. However, the most important example is a sinusoidal distribution, which means, so this is where I am showing the arrows. So, by the way, I must mention these arrows do not, you should think of these arrows as force per unit area, which means if you take an unit area, then the force acting on this total force acting on this particular area is given by the arrow times the area. That is, if you take an let us say a length of magnitude dx, then the total force acting on this length dx is this arrow, which is called the load per unit length times the length of the area. So, this is the meaning of this profile. So, this arrows represents the load, external load per unit length. So, here it follows a sine curve. So, sine curve and cosine curves are equivalent. So, I am assuming sine curve. So, why sine is the most important example? Because of a very powerful and wonderful mathematical theorem called Fourier series analysis. What is that theorem? So, I am going to, so you learn this theory about Fourier series in other courses. So, I am just going to state that the general principle of that any complicated function f(x), any complicated nonlinear function, something like this, can be described by an infinite series or sum of sine and cosine functions. So, you can always analyze them in as a kind in terms of components. So, each each component is a sine profile or a cosine profile with appropriate coefficients, provided the function f(x) satisfies certain mathematical condition. So, if we know the sine and if we understand the sine and cosine profile, then by combining them we can understand any nonlinear profile. One more thing is that when we sort of look at this kind of situations of distributed force, like the nature of, we found that the support, there are different designs of support. Similarly, that is also true if you have a beam. So, for example, this is a beam which is one end is sort of pin joint and the other end is a roller. So, this is supported at both ends. This beam is called cantilever. So, it is supported at one end and the other part is hanging in the air. And then you can have more complicated, and this red arrow is again showing the external load. So, and again you can have a combination of them and have more important design. So, the question is, so what are I interested in this kind of this kind of situation? So, the question that we can analyze the so there could be of course different types of question, but what we are interested in is that given the so we want to interested in calculating the force on the joint. So, there is a practical engineering question. Now, given the external load, and this external load is distributed over an area. So, what we want to do is that we want to replace this force distribution by a single equivalent force with the same magnitude. So, we want to know that what is the magnitude and direction and line of action of the equivalent force, and we want to calculate, and in order to do that we want to calculate the moment that this force is generating, and the equivalent means that it will be clear in the moment. So, these are the things I am interested to know. So, we want to calculate the total torque generated by a distribution of load, and it is easier to do that. A simple trick is to if you can replace this distribution of load by a single equivalent force acting at a single point, and how to do that. So, this is the question. So, this is the question that we are going to analyze in the next lecture. Thank you.